Okay, thanks for joining me. I assume you're here. I assume everything is working. We'll know soon. Um, so, a couple interest, introductory things. First of all, please let me know if you're having any trouble with the technology. Hopefully, if you're seeing this, you're probably not a person who's having too much trouble with the technology. I'll post some things that along those lines too to ask for suggestions or comments. And then secondly, I'll ask you to please introduce yourselves is in the discussion board. I'd like to start getting some crosstalk among people going on the discussion boards. The right way to do that. So anyway, this is the second lecture, and what I want to go through is really talk about how materials have evolved through history and how materials are really a very, very central part of technical development. Want to go through their positive feedback loops that work through this, and I think you'll see what that means as we go, and and that, that there are great jobs in this, and all of this is really very visible with things you might even find in the basement and so forth, and you'll see what I mean by that in a little bit. So this is properties of materials and materials evolution. What I'll try to do in every lecture, try to lead with some learning objectives. And a few things I want to go through is talk a little bit specifically about what we mean by materials properties and what that means in this context, and define some properties that we care about. Talk about how we might measure and report some of those properties, and if you're looking for materials properties, there are actually some pretty good sources of such things. I think it's .org, matweb.org. Possibly it's a com is a good one, and that's a common site that I use myself to figure out what rule of thumb properties of materials are. What's really interesting, what I want to talk about now is there's this continual evolution that it's kind of hard to see if you don't look for it, but if you look for it, by gosh, you can see it's really there. And how have the materials that are available and their properties over time changed? And there are indeed materials with new properties that are available. These have enabled and are key in developing new devices, and this has really enhanced the human experience. The other thing I really want to put in, should be on the learning objectives. I'm going to do an introduction to logarithms, and I'll do this in sort of a practical way, and I'm sure you've all taken this at some point. And logarithmic thinking, I think, is a wonderful way of looking at the world. It's typically not what too many people do, but if you're going to really take the broad view of things, it's a great way to do things, and we do need people that can take the broad look at things. So anyway, here's what I'm talking about. I'm going to talk about a few specific implements going through this. One of these being skis, and we'll go through a few examples, and we'll see how materials have enabled new designs. And if you look back not that many years ago, even I think back in the 1930s and 40s probably, the skis were predominantly wood. They didn't even have metal edges on them, and looked something like that. This comes, by the way, from Wikipedia and Creative Commons. I think that should all be stuff that's copyright free. But skis were simply just wood. It's basically because of what we had, and then bindings that were on them were simple straps, steel and so forth. And in part it was because we didn't have ability to use all these fancy materials. If you go to the sporting goods store today, you can spend a lot of money on skis, and you'll find things that are tremendously multi-material. Usually there's a base, and that base is something like PTFE, polytetrafluoroethylene, which, you remember last time I talked about what polyethylene looks like. PTFE basically looks like this, where you just got, instead of hydrogens off here, you've got fluorine atoms, and that's basically Teflon, and you get thousands of units that make these very, very long chains. It's polytetrafluoroethylene. You've usually got hardened steel edges. And then another thing that's really important, we'll get to this a little bit, is a foam core. Foams are fairly new species in the whole group of materials that have come. And foams are really important. And the function of the foam is it adds minimal mass, but it does provide some connection between the cap and the base. And if you can keep these connected, but keep them a fair distance from one another, what we end up getting is we end up seeing something that's actually very, very stiff, and we can control these properties by controlling this thickness. And that's what you want to do with skis, is you want to control the geometry, control the stiffness, and that controls the ride. So there's all kinds of materials that go into this, and then you often also see active materials. I think last time I talked about piezoelectrics very briefly. Active materials can basically take motion and turn that into electricity. You can absorb that electricity. You can run things, you can damp things, and you even see piezoelectrics. Piezoelectrics that sometimes appear in skis, and I'll try to be a little more careful with my handwriting. Here's another example of how life has gotten better from advanced materials. Here's an old canoe back in the days when a canoe was the difference between life and death, not just a hobby. This is what the native people would use. This is usually made by available materials, bark, sticks, moose hides, what have you, but it's things you could make available, wrapped together with hemp rope and so forth. Very heavy, get waterlogged, could leak, isn't very stiff, isn't necessarily very fast. But this would be your livelihood. You'd spend a lot of time making your canoe, dealing with your canoe. Now if you have a hobby and you care about your hobby and go canoeing more than a couple times a year, you could probably go back and get yourself Kevlar epoxy canoe, and that would cost you, basically a few days of work, whereas this thing might cost you months of work. And this is a far better canoe. Nice example of how life has gotten a little bit better, and these things are light as well. So again, like the skis, you're getting stuff that's better suited for that, cheaper, all those good things. Another example, personal music systems. First personal recordings started becoming available around the 1880s. Thomas Edison was an early innovator of this. Basically what you would do is you'd speak into here, so it'd vibrate a stylus, you'd get an imprint on the wax drum, and you could get that wax drum to play back a few times and get the sound back out of that. And again, this was a very expensive device. You'd be very, very lucky to have one of these in, don't show that message again. Very, very lucky to have one of these in your home. They're beautiful things, but not very utilitarian. Now, state of the art is something that looks like this. It's a huge number of materials in something like an iPod Nano. And you can imagine that there's capacitive display in this, there's memory storage, there's a battery in there, there's little switches, and a huge number of materials. It takes the talents of an amazing number of people to come together in some coordinated way to make this cheaply. And I've got 5 or 6 similar devices in my little office where I'm recording this right now. I'm kind of been a junkie for these. I had an early iPod, and I've had maybe every second or third generation since. So I've got a number of these, whereas I don't think my family has ever owned one of these. So things have become more interesting, cheaper, more multifunctional, smaller, all that. In general, these things have made life better, I'd like to contend. The couple places that are really fun to work as a material scientist are places where people will spend money to allow you to do really interesting, cool stuff. The 2 places that budgets tend to be pretty big are where we have competitions. One is in sport, and America's Cup Yachting. There's a has always been very much a rich man's sport, and kind of anything goes in technology, and the latest and greatest has always been used. I'll talk about that in a moment. The other place that's sort of a competition where we're able to use really advanced materials and do is in warfare, and it's another place where we use the best stuff, are able to innovate, and that actually does drive a lot of technology forward. NASA does a similar thing, and it's also sort of a competitive thing where we want to get there faster than the Russians, for example. But anyway, looking back to America's Cup Yachts, 1851, not that long ago in the broad sweep of history. This is what fastest boats in the world in this size class would look like. You see sails were probably made out of canvas, ropes were probably made out of hemp, wooden hull. Otherwise, it's a pretty spare boat to be as fast and light as possible, but you can only make wood, hemp, nails, and so forth so light. Fast forward to modern times. If you're racing in the America's Cup right now, number one, you need a really big budget. Second thing you need is some really high-tech materials. Again, this is largely graphite and carbon plus epoxy. There's also a lot of Dyneema and Spectra in this. Again, this very, very high modulus polyethylene, very high strength, very high stiffness polyethylene probably makes up the ropes on this. This thing has a very, very high specific strength, very high strength to weight ratio, way, way faster than this boat here. These materials have allowed a very innovative and fast design that you never could have built out of the wood and hemp back in the day. And even in the past, sailboats are actually going through quite a renaissance right now. This is a fairly new thing, winged sails, and that's only been the last about 5 years right now, and these are very hard to sail, but give you very high performance when you're pointing into the wind, and that's always where sailboat races are won and lost, is how fast can you head into the wind, and how closely can you point towards the oncoming wind and still make progress. And these sails that are very much more like airplane sails than the back of these old sails are really the key to making that happen. Again, it's advanced materials that makes all this possible. So just to show that this really has kind of made a pervasive impact on the world, again, let's just consider the last 200 years, which is roughly 8 generations or so, and pretty small span of time when you consider the broad scope of history, and I'll talk about what I mean by that phrase in a little bit. But if you go from I should have updated this, made the slide last year. You can see from 1811 to 2011. Back in the United States in 1811, life expectancy was somewhere on the order, maybe a little longer than that, but 30, 40 years. You get sick badly, you get a bad flu or something, and it's over. But the good news, I guess, if any, is life was kind of harsh anyway. So back then your income was maybe on the order about $4,000. It allowed you to have a few outfits of clothing, allowed you to eat fairly simply. You might have a simple house with a simple roof. You certainly didn't have television. You certainly didn't have a lot of the things we take for granted right now. There wasn't too much to spend your money on either back then. You go back even before that, medieval times. Maybe your fun was once or twice a year you'd get to go to some kind of big Mardi Gras festival, have a stein of ale and a turkey leg, and that's it. Come to today, about the same using the same dollars, average income in the United States is around $40,000 a year, around 10x. So instead of going to a festival once a year, college students that I know usually go out Thursday, Friday, Saturday night. It's like Mardi Gras 3 times a week instead of twice a year. Again, standard of living has gone up. What you do with it is your own choice. And our life expectancy now is maybe 70 to 80 years old. And a lot of this is because we have a greater income. We are able to eat better. We're able to afford food that we know is clean, that is free from bacteria. It's sanitary. Food is plentiful. We don't have people in the United States anyway dying from hunger very much. And sanitation is a big deal because things are clean. People aren't dying from all these diseases. So these things are definitely linked. And again, I'll make the case that I think materials has really been important in that, because that's actually enabled a lot of the equipment that we even use in things like farming and medicine and so forth, that have allowed the standard of living, and that drives the life expectancy. It all kind of works together. So I could go on and think about how materials impact all these things. You can think about medical devices, the way you might have cast up something years ago. You didn't have air casts. You didn't have the polymers that do that. If you wanted to replace a part of the body, there's all kinds of things that are happening right now where we can tailor make things like bone to shape and so forth. All kinds of interesting things happening. Personal transportation, go back even to, say, the jet airplanes came in about the 1960s. That's all been very much available by materials. Air transportation was very expensive. It's something we now more or less take for granted. So personal transportation, air transportation, cans are a big deal. Cans have actually enabled us to eat vegetables in the winter in large measure, keeps things clean. Buildings and roads, sporting goods, musical instruments were sort of traditional, but even things like electric guitars rely on wire and so forth. Art, armor, all these things. Every field you look at is really paced in large part by the materials that are available to make things. So what makes next generation stuff? And I think there's really three parts to this. First of all, the thing I've been harping on are the materials that are available. And that's important. But it's not everything. The other thing that's important is a design, and our designs keep getting better and better. And again, designs have been really helped a lot, by example, by computation. And computation, in a lot of ways, was itself made possible by materials, because we've had things like silicon have come along, and we've learned how to harness the properties of silicon to make microprocessors and very small computers. That ends up allowing us to make better materials, allows us to design better, and so forth and so forth. There's a positive feedback loop that goes on through that. And then when we have higher performance materials, it enables new kinds of designs. The other part of this that I think is really important to add on to this is manufacturing. Because if you can only have a small amount of a material available, that may not really help you. But by manufacturing and automating things, we have, again, more materials, more computers, better design. And all of this fits into really a positive feedback loop where better materials enable better designs, can allow better manufacturing processes and so forth. And the whole process tends to speed up and speed up and speed up and speed up. And all of this really requires technical literacy. This really, I think, embodies all of STEM, is right in that, and right what's been going on in history is during our lifetimes faster than ever before, really. And this is stuff you can really see just looking at the products of the past several years, just as I've shown before. And I think you can tell your students that if you want to be part of all of this, the only way you do it is by getting some training and the training you need is mathematics, physics, knowing how to build things. I'm a big proponent of being able to do things with your own hands, even if things like an iPod Nano you can't make with your own hands. Somebody has to be able to make the first prototypes, and doing those early prototypes is really important, and there are loads of good careers in that sort of stuff, sort of thing also, and that's all based on people being able to do things with their own hands. Okay, so here's the other theme I talked about, linear and logarithmic thinking. Almost always in mathematics we focus on this. We focus on things that are 20% greater or a little bit different than the other things. We don't usually spend a whole lot of time of thinking of things that are broadly different. And I think it's really important that we do that. For example, if you're going to think about the national debt, you're going to think about overall how much carbon we're putting into the atmosphere every year. If you're going to think about problems like this, you've got to make big extrapolations and think about numbers that are in the billions and trillions. And we have a hard time doing that. I have a hard time doing that, but I think logarithmic thinking helps you do that, and being able to scale problems down and put things in a per useful, a per capita, or some other smaller number. So anyway, point I want to make right now is, and we'll come back to this in these other lectures, is one of the great challenges in material science, which makes it, I think, a wonderfully interesting discipline too, is you have to think about it on very different scales, and I'll talk about what I mean. Right here I'm going to talk about length scales. I'm also going to talk about time scales in separate slides. And here we're going to consider large differences more than small ones, and that's going to be a theme in this class, and I'll make the case again that materials is a great way of thinking about these big differences. And linking length and time scales is really a large, or really the dominant problem in material science. You're gonna see this, and this is what I think is one of the things that really separates material science from a lot of other disciplines. So here's time scales, and this is the logarithmic scale. Remember logarithmic scale, for example, you're going from a second to 10 seconds to 100 seconds to 1,000 seconds to an hour is 3,600 seconds. And so anywhere you put on this is a factor of 100x. So if you go from a year, this distance from here to here goes 100x. So a human lifetime is a little less than 100 years. So you can see how an hour to a year is a lot bigger difference than a year to a human lifetime, for example. And it's actually a very interesting way of thinking in a lot of ways. So let's think about material science. We know what materials are. Materials basically are crystalline things, or you might imagine as a bunch of iron atoms that are all sitting here together, and somehow we might have a force on this, a load under it, and over time these things can actually creep. But this can actually change its shape. These crystals can change their shape. We might talk about that as the course goes on. But what I want to focus on right now is each of these, you can almost imagine as being masses held together by springs, and these things are vibrating. There's a vibration period. It's on the order about 10 to the 12th vibrations per second. And every now and then, one of those vibrations, one of these things might pop out, might move to a different location. It's happening on such a fast time scale, we have a hard time thinking about it. But really, it's those fundamental processes that might tell us eventually when a turbine blade breaks or something like that. So we somehow have to connect these really fast processes to things like the life of a turbine blade, which is on the order of years, we hope. So anyway, just to put this on logarithmic scale, atom vibrations happen here on the order of a picosecond. We end up going 1,000 picoseconds to get to a nanosecond. Nanoseconds are maybe the range of a pulsed laser that you might get at. Microsecond is 1,000 times faster than that. Some of the fastest things we might be able to see is like the fastest thing we can resolve is a little bit longer than the contact time of a baseball on a bat. And all of this stuff is basically, invisible because it's just too fast for us, and we can build oscilloscopes and do some other things, very, very high-speed photography to show these things. But things that are too fast are hard to understand, but important. And going up from here, we try to turn these shortest resolvable instance into engineering problems. How might a bridge corrode over time? How long might a piece of glass last before it creeps to a shape that's unusable? So timescales are important. This is a little bit abstract. Length scales are maybe a better thing to think about. This is really important in materials science. Protons are down here around a femtometer. Picometer is down here. The smallest distance we really care about in material science is really this atom repeat distance. And that's on the order of about 0.25 nanometers, which is about 2.5 angstroms, which is equal to 2.5 times 10 to the minus 10 meters. That's what we care about. And so going back to that picture of having these crystals that have these ordered arrays of atoms, so these things are all sitting about 2.5 angstroms apart. You might see some of these change chemistry, and the smallest clusters we care about are down here, a few nanometers in cross section. Bacteria are down here. Visible light wavelength is down here. Smallest thing we can see with our eye is on the order of about 10 microns, maybe about 20 microns in diameter. That's about the same size as the smallest, about the size of the smallest thing we could see. It's about the size of a typical metal crystal diameter. And these crystals then, so these form crystals. These crystals then pack together and basically form the polycrystalline metal that might make up what we're interested in, and then the beverage can walls, car door auto panels, width of a fingernail goes up here. And what we're really trying to do is connect what goes on here at this level to something like human level, the height of a human. And there's, again, from here to here, about 10 orders of magnitude. 10, so it's like almost a difference between a bacteria and the height of the Empire State Building. Big differences go into that. So anyway, that's kind of an important way of thinking too. And when we talk about microstructure, we'll go back to these logarithmic scales again. So another interesting thing to think about, made the point that these feedback loops happen all the time. Ray Kurzweil has a book called The Singularity is Near. It was kind of a hit some years ago. I think has some very interesting ideas. I don't buy off on all his conclusions. But what he's done is he's picked what he considers to be a lot of the really important events in the broad history of life, starting with life itself, going from cells to human ancestors that walk upright, to where we form cities, where we do agriculture, have city-states, industrial revolution, and so forth. He's taken those and written down the big events that have got us here, and plotted the time before present, and plotted the time from one event to the next event. Both of these, again, on logarithmic scales, factors of 10 here. And what we can see is back here in the day of going from, say, a multicellular organism to reptiles, took on the order of, the time between these events here is on the order of 10 to the 8th, about 100 million to a billion years it took to get from these small cells to reptiles. About 1 billion years was taken there. And that happened about a billion years ago. If we go forward, humans have only arrived on the scene about on the order of 1 million to 100,000 years ago. And then fairly quickly we started forming cities, developing agriculture, developing writing in the wheel, city-states, doing printing in the experimental method. And really that only came up, printing the experimental method was less than 1,000 years ago. And these things keep happening faster. And part of it is once you know how to print, you can start to transmit information. Once you transmit information, you can start the Industrial Revolution. Once you have better materials, you can make things like computers. Once you have computers, everything just speeds up, speeds up, speeds up. So we've gone really in, my lifetime, really just pretty much from the computer to the personal computer to the internet to massive connectivity to things like YouTube, and massive changes are happening right under our feet, and they are technical, and this is what I really think you want to get your students in on. Again, if you look at it this way, into this broad scope of history, things are happening. They're happening faster and faster and faster. And Ray Kurzweil's idea is it's not going to be very long, and there's going to be some kind of a major breakthrough, because this thing is going towards basically going to be happening where there's a new event happening every second or so if this pattern continues. And pretty soon that means we'll have robots that are way smarter than us. There could be robot uprisings, all this stuff. Or maybe if it's not so bad, maybe we get to the point where we figure out how to give dramatic, really understand our cellular biology and can give dramatic life extension, and we might ourselves live to be hundreds of years old and become immortal and put our brains on hard drives, and who knows, and that's sort of the idea. But there is no doubt that technical change is strong, and it is accelerating, and there are these positive feedback loops. And if you want to be part of this process, you need to know something about this. That would be my thing to students. Okay, so let me get from some stuff that's really kind of flaky to really flaky but important to real materials properties. And what I want to do now is define what we mean by properties. And really, an intensive material properties of materials is an intensive property. Excuse me. Let me start over again. A property is an intensive measure of a material's fitness for a given purpose. So let me first of all say what I mean by an intensive property. An intensive property is one that does not depend on amount. For example, if I say I have 10 grams of that, that depends on the amount. 10 grams, so something that's 10 grams is going to weigh more than something that's 5 grams, obviously. But what I care about is something like the material conductivity, which is an intrinsic property of the material, something that does not depend on the amount of that material that we have. So example, acoustic properties, resonant sound wave speed might be something there, a mechanical strength or stiffness, electrical, something like conductivity, atomic, is it radioactive maybe, chemical, for example, thermal properties, for example, heat capacity, thermal conductivity. These are all intensive properties, and these are things that we need in engineering. Some of these properties are very easily and very strongly changed by the structure of material. For example, strength, toughness, conductivity, all can be changed by basically putting more dislocations in the material, putting other phases in it. Those are all ways we can change some of those properties. Other things are kind of hard to change, and there's kind of some art built into these phrases, but some properties, for example, density, elastic modulus, these are really developed really by the interatomic bonding that happens. So it's really hard to change these, whereas these properties have a lot to do with the defect structure, and we can control the defect structure to a pretty large degree. So these can be changed, these can't be changed so much. And we may, if anybody has questions about any of this is something we could go through. And this actually, bring this up because I know in some of the standards and benchmarks, there's language that talks almost exactly about this point of what can you and can't you change. And I'm not sure exactly what degree, what depth they expect this to be gone into. But that is something that's in the Ohio standards and benchmarks, this aspect. So I'm going to consider two specific properties and link this together with other things in this lecture, what products are available and logarithmic scales. So the two I'm going to talk about, one is strength, and strength we'll often put something like on there like yield strength or failure strength or something like that. And usually what we're talking about is force per area as a strength. So I've got something like this. I could imagine saying, okay, I can measure this area here, put some kind of force on here, and when it breaks, I can call that a strength. And if I want to double the force I can carry, I should be able to just double that cross-sectional area. And so the carrying force would be an extensive property, depends on how much, but the strength is an intensive property. The other one's density, usually we call it rho, and rho is basically just, so density is an intensive property, and the extensive property that goes with it would be just weight, and weight would be the total mass of something. Density is the mass per volume. About twice the weight, you just put in twice the volume. Okay, so now what I'm going to do is take these two properties, consider how they changed through history, and I want to give acknowledgement to Professor Michael Ashby at Cambridge University. He's published this, and I'm going to shamelessly use his stuff. And we're allowed to use this by teaching. We've paid some license to use the software at Ohio State on this. And here what we have are the universe of available materials back in 50 BC, where on this axis we plot strength. On a logarithmic scale, you see orders of magnitude going this way. On this axis, plot density. Again, one order of magnitude going this way. And this was what was available back then. You had your natural materials, which included things like wood, and you can see different kinds of wood, and different kinds of wood have different densities and different strengths. Balsa has low density and low strength. Ash is pretty high density and pretty high strength. And this is woods parallel to the grain, perpendicular to the grain. Cork has modest but low density, but basically very low strength, for example. You also had ceramics and glasses. We could make a nice, pretty hot fire. And with that, we could make brick, we could make some pottery, make stone, make glass. We could make things with shells, natural material, bone. These generally had higher densities. Again, all these things had fairly modest strengths. And then back in those days, we could also refine some metals. And gold is nice because if you could find it, it naturally doesn't want its oxide. It is available in the pure gold state. We also figured out how to get bronze and copper and so forth from ores. And we could get these things again at higher density, modestly higher strength, actually significantly higher strength. You can see this is 100 megapascals, and we could get things here that might be 400 or 500 megapascals, four or five times stronger than ash. So that's kind of a big deal. And you can see everything here tops out maybe here at about 500 megapascals is about the strongest materials that you could end up getting. There's a fairly limited menu of them. Okay, so now what I'm going to do is I'm going to change slides. I'm going to put materials available later in history on exactly the same scale. And here's what you have in 1945, long way forward. And you can see now you've got your strongest materials before were about 500 megapascal. Now you've got a whole bunch of alloys that are up here stronger than anything that could be developed back then by about a factor of 5. Um, Again, we have natural materials about the same set. We've got a whole new class of materials added, polymers and elastomers. You're seeing bakelite, epoxy, acrylic, rubber, polyethylene, things that didn't exist before. You also are getting some ceramics and glasses that didn't exist before. You're now seeing steels that didn't exist before with very high strengths. Titanium alloys didn't exist before. Aluminum alloys, if they existed, have become much, much, much less expensive because of innovations in how we manufacture and process it. So there's a wider menu of materials available, and the materials you have generally have higher strengths as well. There's a lot you can do to tailor those things. If you go to present day, there's many more things available. You've got a whole bunches of classes of ceramics. You can get industrial diamond, industrial alumina, silicon nitride, silicon carbide. And remember, back in 50 BC, our strengths were limited here. 1945, our strengths are limited here. You're seeing things that are order of magnitude stronger than what's available just in 1945. You're seeing new classes of materials and composites, all kinds of new polymers available. And again, if we just kind of go backwards, just do it like a movie, you can see the space that's taken up. 1945, you can see the globs, and way more material, way more options are available today. Again, this enables designers to do really cool stuff. And then when they do that cool stuff, we have the aha moments, and allows us to process other things. And all kinds of these positive feedback loops happen, and technology marches forward. I think it actually is a great time to be an engineer right now. It's lots of very interesting things happening. And you can see this profusion of all kinds of interesting new materials and new technologies. And again, logarithmic scales are there, and you can think very broadly about this. And another great class of materials is foams. Foams are a big deal if you're making a helmet, if you're making something, bedding, all kinds of things. Foams, biological interest, all kinds of foams have come into this. There's all kinds of ways of engineering with this, and we actually have metal foams that are coming in as well. All these things have just outstanding potential, and the designers are really just learning how to take things like metallic foams and do interesting things with them. So anyway, here's a challenge for your students. And this is what I bring up in quiz 2, is what I'd like you to do is consider some engineered device that's been around for a long time. Ski, for example, something maybe you could find in the garage. And I think a great thing for students would be to possibly take that device apart and think about how that thing is enabled by the materials that are available today, and maybe even how that thing might look different another 20 years from now. And I guarantee you they will. And even if you just look at the iPods I've had since they've come out, the ones that stored a lot of music had been on a disk drive in there, a small one, and now it's all solid state device. I mean, it's just incredible how this stuff has changed and is continuing to change. And so you can consider any of these engineered devices that have been around. And this is something that would actually make a great inspirational, I think would make at least a decent inspirational homework assignment. Consider something. You can use Wikipedia. You can use all these resources to figure out how the materials and design have changed and why they've changed and who those people have been that have pushed that. And they're very ordinary people that blend into the crowd that have done these really remarkable things. And you could discuss how the materials have made that evolution possible, and that's what I ask really in quiz 2. The other thing I ask in quiz 2 that I didn't write down is please use the discussion board to introduce yourself. And we've had one brave soul do that so far. I haven't asked for it long ago, but I do want to build a bit of a community among this group here, even though we may never physically meet. But I think that's the right way for all this to happen. Two other things that are related to that. One is something that I really enjoy. The guys, Thomas Thwaites has done this thing called the Toaster Project. There's a book, there's a TED Talk. Start with the TED Talk. The book is also actually hilarious in spots. I think it gets a little, maybe preachy is quite the right word towards the end for my taste, but it gets a little changes track. But basically, it's a guy who is his final bachelor's project in a design school decides he wants to build a toaster from scratch and tries to create the materials that go into the toaster. And he tries to create the plastic, the metal, the mica, and so forth. And it shows how technology does work and how what many years ago, you go back to early 1900s, pretty much whatever somebody could do, anybody could do. There weren't that many specialized things. Now everything is so specialized that it's almost impossible to make a toaster from scratch. There's a book and a TED Talk. I encourage you to watch the TED Talk. The other thing I want to kind of point out, Todd Bolenbaugh from Toll's Career Academy has also put together a Math Sci teacher, and I hope it's okay I put his name on there. He's kind of anonymous on it, but he's put, I think, something like about 100 of the standard demonstrations that are used in the ASM materials education material onto a YouTube channel, and this is also fantastic. And what I'm going to try before I go is see if I can click on that, and let's see. I'll go out on that. If this crashes before then, you'll know why. And the way this is set up, it's not going to work very well. The movies won't play very well going through, but it shows all this stuff, the CAN demonstrations, cold welding, looking at crystallization of polymers, the iron wire demo. So if anybody wants to brush up on something, this is actually a great way to do that. And thanks thanks to Todd for doing that. The other one, I'll go back to, is this TED Talk. Is also fairly incredible, and we'll just open up the site. But again, this is how I built a better toaster from scratch. And again, it's I think a great thing. If you haven't looked at TED Talks, they're great fun too. I think many people have. Okay, well that's it. We're 2 lectures in. More to come, and look forward to further discussion. I'm going to be taking some of the stuff that appears in the quizzes also and bringing that on forward through other means. So I believe that's all, and I will post another lecture in a week or less. Take care. Bye.